Perhaps the best and most important application of the simple harmonic oscillator potential energy is in understanding molecular vibrations. So just to show you what I mean, consider the following. So consider a molecule like hydrogen bromide, HBr. And if I were to draw a picture of it, I might represent it in the following way. It turns out the bromine is a much bigger atom, and then there's a much smaller hydrogen atom. And I can actually get away with representing their interaction very much like a spring. And so I'll draw actually a little spring between these two atoms. It turns out the molecule can vibrate. So, now, I picked HBr for a particular reason, namely one that makes the analysis a little bit simpler. So, namely, we can make the following approximation. So we assume the H atom is moving. And the bromine atom is fixed in place. This turns out to be a pretty reasonable approximation because there's a large mass difference between H and Br. If you go and look up a periodic table of elements, you can find out that the mass of the bromine is about 80 times the mass of hydrogen. So it's a pretty reasonable approximation to consider bromine fixed, and then just think about the movement of this one hydrogen atom. Now, before I go on, I should mention that we can generalize this to molecules where this approximation isn't true. We can do it in particular for diatomic molecules, which is probably actually the most common case. So things like nitrogen gas that we all, that's most of our air. Nitrogen is N2. Similarly, to be alive, we need oxygen, which is O2, right? And you can do things as well with, either chlorine gas or Cl2, iodine, I2. So the way to generalize this this treatment to molecules where the two atoms have close to similar masses or equal masses, you'll actually learn that in physics 311. There is a way to sort of still reduce this two-body problem to an effective one-body problem. In 311 you'll actually talk about it in the context of gravity and planetary motion. And so using, analyzing orbits of planets, you use Newton's second law and ideas about angular momentum. And technically, right, even though, they're pretty good, even though, right, it's really the center of mass of the system of a star and a planet that's fixed, to pretty good approximation, the sun is orders of magnitude more massive than, say, the Earth, and so you can get away with treating it as a one-body problem. But there is a way to generalize it, which you'll learn when you get to 311, probably next year or your senior year. But that's an aside. So why can I think about this as a spring? So why? So the answer comes from trying to sketch in a little bit more detail how an actual intermolecular potential energy looks. And then it turns out that nearly any potential energy that has some sort of stable equilibrium can be modeled as a harmonic oscillator. So if you try to sketch the actual intermolecular, interatomic potential energy between two atoms as a function of the radial separation r between them, you get something that not atypically looks something like this. Let me unpack this for you a little bit. Right, there's a short range repulsion. If you there's a very high potential energy. If your r is very small. And this you can sort of fundamentally think about. It's going to be really, really hard to push two atoms very close together. And there are a bunch of reasons for this, right? You know that both of these atoms have electrons, and if you push them too hard together, those electron clouds, and even closer together, if you have their nuclei close together, there'll be strong repulsive electrostatic interactions. There's also a long-range attraction out here. And that, right, so this is what you might have learned about in chemistry as van der Waals forces. And those also are fundamentally electrostatic in character. They have to do with the interaction between sort of fluctuating electric dipoles. And so you might talk a little bit more about that in upper level E&M. But sort of in the middle, right, you sort of the competition between this repulsion and the attraction gives rise to something that has a minimum like this. Now, however, near the equilibrium, so if I label this equilibrium here as R0, near that equilibrium, my potential energy actually looks pretty quadratic. So let me show you what I mean. If I draw in, sort of try to draw in a parabola over this, right? I get something like that, right? As long as I don't get too far away from r equals r0, near the equilibrium, V approximately quadratic near r0, right? So that means that I can now basically bring in everything that we figured out about the quantum harmonic oscillator to draw in what the energy levels or the energy eigenvalues here might be, and they might look something like this. So maybe here's my ground state, and I can draw in a bunch more energy eigenvalues right there. Formally, right, you can sort of see why this is the case by Taylor expanding the potential energy. Let me sort of take a quick aside to do that for you. So this is maybe a little bit beyond the class, but I think most of you should have seen Taylor series by now. So formally, Taylor expand so namely, near R0 I can write the potential energy in the following way. So right, I can say that V of R is approximately equal to V at R0 plus dV dr evaluated at R0 times R minus R0, right? And then my next order term is going to be my quadratic term in Taylor's theorem, which will go like 1/2 times my second derivative. So d squared v dr squared evaluated at r naught times r minus r naught squared. So here's the thing, right? If I have a minimum in my potential energy at r equals r naught, right? What's the derivative of my potential energy at a minimum? Well, like you learned in calculus, for any function at an extremum, the first derivative vanishes. So that kills off this entire term here, right? And aside from this term, right, which is essentially just an offset, right, the first sort of non-trivial term in the potential energy is this thing, which is in fact quadratic in r minus r naught. And this, in fact, the second derivative of my potential energy actually kind of acts like a spring constant, right? So, and some people might even call this an effective spring constant, right? Some k effective. And we might have a homework problem where you consider this an example of this in more detail. But anyway, so the key takeaway is, right, for any potential energy that has sort of a local minimum, I can approximate it as being approximately quadratic, or in other words, being a simple harmonic oscillator. So there's one other fact that I just wanted to mention, which sort of underlies most of the applications and the relevance, which is the interaction of such a molecule with light. So in particular, absorption of a photon with the right energy, namely the energy equal to the spacing between two of these energy eigenvalues, with energy right, so let me label that here again. Right, can cause a transition from my ground state n equals 0 to n equals 1. Similarly, if you were already in an excited state, so if you were at n equals 1, you could go up to n equals 2, or you could even generalize this if you were in the ground state and absorbed a photon of energy 2h bar omega, you could get from here up to there. So this is really important because this means that you can detect evidence for these molecular vibrations by measuring how these molecules interact with light. That's spectroscopy, right? So I can perhaps imagine doing an experiment where I shine light through a sample of a gas, of HBr gas, and look at what comes out, and look to see if there are particular wavelengths of light, that is, particular photon energies that end up getting absorbed. So thinking about this sort of thing turns out to be super relevant if you are, say, you're an astronomer and you're trying to understand things like stellar atmospheres, if you do planetary science. But there's sort of an even more important reason that all of us should care about this. Now, namely, this has a huge impact on climate change. So, in particular, right, so you've probably all heard of greenhouse gases, right? So things like carbon dioxide and methane, right? That preferentially absorb infrared radiation when it's reflected from the surface of the Earth. Now, For a molecule like carbon dioxide, it's a little bit more complicated because it's not just like two bodies. You have CO2 is an oxygen in the middle. A carbon in the middle and two oxygens, and something that has like three things can do more interesting vibrations. Right? You can have wiggling modes, or you can have like symmetric vibrations or anti-symmetric vibrations. So again, in mechanics, you might talk about sort of how to find the normal modes of what are called the normal modes of vibration of sort of a molecule that has more than two atoms. But it turns out though that once you do that, pretty much all of the formalism of the harmonic oscillator still applies. And so again, this turns out to be a very relevant problem for just understanding the physics behind why we should be mindful about greenhouse gases in the atmosphere for the long-term sake of our planet. So we'll close today's class with a whiteboard exercise where you'll estimate, based on some spectroscopy data, the spring constant in HBr. So I'll make another video where I'll work through that whiteboard problem, and then so we'll have a shorter class on Wednesday and Friday, so you have some time to prep for the exam and take it. But then the next thing we'll look at is scattering and tunneling. And then in about a week we'll sort of wrap up our introduction to 1D quantum mechanics, and then we'll turn to studying the quantum mechanics of atoms.